Hi and welcome to the lectures by Dental Amaze Academy. Today I'm going to discuss with you something known as phase diagrams or equilibrium phase diagrams. Now the importance of this topic is that it is being asked, one of the questions has been asked in the NEET 2020-21 and this seems to be a little difficult for some students. Don't worry, it will be made easy for you. Okay, now this you could see here. Okay, you could see this diagram here. Okay, this is the equilibrium phase diagram for silver palladium alloy. Okay, silver palladium alloy. Okay, don't panic. Now, if you see this, you will find it very confusing. Don't worry, I'll explain this to you, and once you understand it, we'll explain this diagram in detail. Okay, so before going into such complicated diagram, let us simplify this and take another element which is or another alloy which is copper nickel alloy. Okay, one of the very simplest of alloys. Now before that, okay, I'll not go into the definitions and all those now. Okay, if I go into the definitions, it will become complicated. So first let me just give you how is this phase diagram being formulated. Once that is done, we'll go on to the definitions and detailing. Okay, so let us take copper nickel alloy. Okay, copper nickel alloy. And if you know that copper has got a melting point, so if you consider copper, it has got a melting point. Okay, I'll just write as T, okay, Tm, melting point. It has got a melting point which is in the range of 1085 degrees Celsius. Okay, 1085 degrees Celsius. Whereas if you consider nickel, okay, nickel, the melting temperature is the 1453 degrees Celsius. Okay, 1400, so it's 1453 degrees Celsius. So this has got two different melting points. Now if you join these two metals or elements and you get an alloy, they have got a different melting range, isn't it? Now let us see a diagram here. Okay, come a little down. Okay, let it be here. So if you consider this as a y-axis, okay, let us take this as a y-axis for a particular graph. Okay, and we discuss about the copper. Okay, and I've told you the melting point of copper is 1085 degrees Celsius. So let this be that 1085. Okay, 1085. So above this temperature, copper is going to melt and is going to be in a liquid phase. Isn't it? Copper is going to be in a liquid phase. Now, on the other side, let us consider nickel. Okay, let us consider nickel here. Okay, now you're going to consider nickel here. It's pure metal separately. Okay, there has no being alloying. Okay, no alloy has formed. And we have seen that the nickel melts at a temperature of 1453 degrees Celsius. So definitely above the range of copper, anyway above 1085. So let it be here somewhere. Okay, 14, like somewhere here. Okay, 1453 degrees Celsius. Now what we are going to do is we are going to alloy them. Okay, we are going to alloy them. So we have to combine the graph, isn't it? Now we're coming on to the phase diagrams. Okay, now, and we have here below composition. Okay, we consider the composition because when we alloy them, we have to 50-50 of copper and nickel, or you can mix at 30-70 anyway. So let us take the x-axis as the composition, and we need a unit for composition, and the unit we are considering here is weight percentage of nickel. Okay, we can take copper also, but for a reference range we are taking weight percentage, how much weight of nickel is there. Okay, how much weight of nickel is there. Now if you consider that and you see this particular center, how much nickel is there, how much nickel is going to be here? It is going to be 50% nickel at the center, 50% nickel. And you come on to the extreme left end where you have copper. Here the nickel is going to be 0%, isn't it? 0%, because there is only copper. And you come on to the extreme right end, you'll see that it is 100% copper. sorry, 100% nickel. Hope you understood. Okay, we are taking nickel as the unit, weight percentage. Okay, we are not considering copper. So in the center you have got 50% nickel. At the extreme left end you have got 0% nickel, and at the extreme right end you have got 100% nickel. Okay, now we are alloying it and we are considering a composition which has got 50% nickel. Okay, 50% nickel and 50% copper. And let us see where will be the melting range. Where will it melt? So I'm not doing any experiment. I'm just simply extrapolating the graph. Okay, I'm simply extrapolating the graph, and I expect it to be somewhere in this range. Okay, I'm expecting it to be somewhere in this range, in the center. So it seems to be somewhere here. Okay, the melting point of this alloy, let us expect, okay, it is not correct, it's not absolutely correct, I'll explain it to you, but let us expect it to be here. And what will be that value? The value is going to be the average of the two, that is 1085 plus 1453 divided by 2. Simple, which is going to be 1269 degrees Celsius. Okay, 1269 degree Celsius, which is the average. Okay, which is this value, the pink one. Okay, which is 1269. Let us take it like that. Okay, now, so exactly it is not at the center. Okay, where I have drawn it is slightly moved towards the left, but let us take it to be at the center. Okay, now, but what happened was, when I did experiments, I took the alloy, I made the alloy, I did the experiments, and I found out that the actual melting point of the alloy, which has got 50% copper and 50% nickel, was slightly, the melting began somewhere here. Okay, slightly below that. And astonishingly, it even continues slightly above that. Okay, but when you consider the alloy, when you consider pure copper, which melted at 1085 and it melted completely at 1085. When you consider nickel, on the other side, it completely melted at 1453. But when you consider the alloy, it started melting at a particular point and it continued to melt till that another point. That is what the speciality of the alloys. It has got a melting range. Okay, not a melting temperature. Okay, now let us take 75% of copper nickel. Okay, we are taking, what is the unit of a nickel? So let us take 75% nickel, which is somewhere here. I'm marking here 75%. Okay, nickel, and the remaining 25% is copper. So what will be the melting? What is expected, or what are we expecting? We're expecting it to be somewhere here, isn't it? Somewhere here. But actually it was not like that. When experiment was done, it was slightly below, started melting, and it continued to melt slightly above that. Now if you take on this end less than 50, that is 25% nickel, means 75% copper, you are expecting the melting range to be somewhere here, isn't it? But when experiment was done, it showed that it started melting somewhere here and it ended melting somewhere here. Okay, now, so this is what you got a graph. Okay, that is you're going, so that means, now another thing, when I said it starts melting means what? So you could see or understand it that it's completely solid here, isn't it? It's completely solid here, and it is going to be liquid here. So melting starts and liquid here. Okay. Now, what I'm going to see is that, or what I'm going to do is that I'm going to connect these lines. Okay, I'm going to connect, definitely not very perfect, and I'm going to connect the other end also. Okay. Okay, so it should be like, it should go like this. Okay. Okay, now should be the green point should be, the green dot should be somewhere here, not there. Okay, it should be somewhere here. Okay, so what we got was this kind of a graph, and the top line, the green line, is called liquidus line. Okay, and the bottom line is called the solidus line. Now, what is it? What does it mean? Now, that is above this line, above this bottom line, the alloy started, based on the composition, the alloy started melting. Okay, it changes from solid to liquid, starts melting. Okay, it starts melting. And now when it reaches this line, the above line, green line, it is completely melted. Okay, it is completely melted. So the bottom line, it started melting, and the top line, it is completely melted. Means, what is the indication here? That means above the liquidus line, the alloy is completely liquid. Okay, below the solidus line, it is completely solid. So what about in between, in this green shaded region? It is going to be solid plus liquid. So this solid plus liquid. So this is a phase diagram to understand. Okay, very simple, isn't it? There is no complication at all. That is, alloy melts at a different rate. So this is what this diagram is all about. But now it is a different variation. The graph is not exactly, because the melting ranges is varying. Okay, I've just made it simplified for you, taking the copper nickel alloy. Okay, so this is what is the phase diagram. Okay, phase diagram. Now, so you got it. Like, two things are varying here. One is temperature, other is composition. Okay, so what is phase diagram? That is, or what is the purpose of phase diagram? Phase diagram is used to identify the phases present in an alloy system for different composition and temperature. Okay, that is to identify the phases, identify the phases of an alloy for different of an alloy. So it's important to be an alloy. It should be an alloy, isn't it? Of an alloy at different composition and temperature. Okay, so different phases. At what phase it is? It is in a liquid phase or it is in a solid phase at a particular composition. So like, now you take a particular composition of 50%. So how much is solid, how much is liquid? All those you can, at what temperature it is liquid, it is solid. So that is what is the purpose of phase diagram. Still we haven't come on to the definition. I'll explain this particular graph, and then I'll come on to the definition, because this is the graph given in your Phillips, okay, Anusaris. So maybe they can ask you any question based on this. So I'll explain this graph a little bit in detail. Okay, so now this is the graph showing the, as I've told you previously, it's an alloy of silver and palladium. Okay, silver and palladium. Okay, and the composition we are going to consider here is going to be 65% palladium and 35% silver. So where exactly that is going to be? So that is 65% palladium. So we're considering composition weight percentage palladium. So this is going to be, this line is going, this is going to be 65%, or I would say this particular point is going to be 65% palladium. That means the remaining is silver. So this line, that is the PO line, is a line which corresponds to the actual alloy we are considering. Okay, now see this graph. At a temperature of 1500 degrees Celsius, this particular alloy is completely liquid. Okay, it is completely liquid. That is, it is completely liquid. Okay, now when you come down at a temperature, if you want to consider, that is at 900 degrees Celsius, for example. Okay, this is going to be a completely solid. Okay, now what we are going to consider is that at a temperature of 1400 degrees Celsius, what is going to happen? So this is 1400 degrees Celsius. Okay, now let us see. This is the, we have to see what is the composition. So this is the line which corresponds to the 1400 degrees Celsius, isn't it? No confusion, isn't it? Now at this phase, what you can see here is, when you see your M here, you could see, now you know very clearly that this Above this line it is completely liquid, below this line, the second line, it is completely solid. Means what? At 1400 degrees Celsius, this alloy at a particular point here, okay, at a particular point here, it is a liquid, it is liquid. But when it comes to here, at a particular point here where it has started to solidify, that means at 1400 degrees Celsius the first solidification takes place. Now here we are considering the solidification. Previously we considered the liquefaction or melting. Now we are solidifying it from a higher temperature, we are bringing to a lower temperature. So first solid forms. Now the funniest part is that when the first solid forms, this is the importance of phase diagram. When the first solid is formed at 1400 degrees Celsius here at this point, is the composition going to be the same as 65-35? No, that is the fun part. You just extrapolate here and you see that the composition is 75% palladium and 25% silver. Okay, this is a little higher level I'm teaching you. Okay, usually you just need to know what is this diagram is. Okay, solid, liquid is line, solid is line. What is where is solid plus liquid? Where is liquid? Where is solid? That's it. But now it is going a little bit higher level. So at 1400 degrees Celsius, you will see that don't complicate yourself. If you complicate yourself, you're going to get into trouble. Very simple thing is that if you see this particular line, okay, at a particular temperature of 1400 degrees Celsius, you will see that at point R, it is liquid. But when it comes to like at a particular temperature, which is 1400 degrees Celsius, it starts first solidification. Okay, it starts first solidification, and the composition varies. Now let us consider another area, which is 1370. That is between the two ranges. Okay, that is the midway of the midway of melting of this particular alloy, that is 1000. So let it be here 1370 degrees Celsius. Okay, 70 degrees Celsius. So this is the line. Okay, this is the line. Okay, so it should be till here. Okay, now if you consider this line, let me rub the previous one. Okay, if you consider this particular temperature, now you could see that this is the point S. I'll use a different color, black. This is the point S. So it has got both solid and liquid, isn't it? It has got both solid and liquid because it's in the midway. Okay, and that has got a different composition. That's what I want to tell you here. It has got a composition which is, yeah, the one which corresponds to the PO. Okay, it is solid and liquid at this particular phase. But when it reaches a particular point where it is much more toward the solid, that is point W, the composition is different. Okay, the composition is somewhere in the 70 range. Okay, now if it is much more towards the liquid side, at the same temperature, the temperature is not changing at 1370, the composition of this alloy is more towards the like less than 60, somewhere 57% of palladium. So this is what you have to know. If they ask you at a particular temperature, what is the composition? That's the purpose. Okay, that's the purpose of, or they can ask you in different way also. But if they ask you at a particular temperature, okay, what is the composition of the solid phase? What is the composition of the liquid phase? What is the composition of a solid plus liquid phase, equilibrium phase? Okay, or they can ask you like what is the a phase at, or what is the phase of the alloy at a particular temperature and composition. Okay, that is what the purpose, isn't it? At a particular temperature and composition. So let me explain to you. Like for example, at a particular temperature means let us take it 1400. Okay, and they're saying that the 1400 degrees Celsius and the composition is 65% palladium. What is the phase? The phase is predominantly liquid, isn't it? It's predominantly liquid, or we could call it as liquid. Now, at the same temperature, okay, when the composition is 70 or 78 or 78% palladium, 78% palladium, what is the phase? The phase is predominantly solid. So this is what I've told you. That is to identify the phases of an alloy at different composition and temperatures. That is the purpose of phase diagrams. Okay, hope you got this. It's very simple. Now we are going to go on to the definition, because without explaining all this, if I explain the definition, then you will find like very confusing. Okay, now let us go on to the definition. The other name for the phase diagram is constitution diagram. Constitution diagram. Okay, constitution means the composition, or equilibrium phase diagram, or equilibrium diagram. So now, what is the definition? The definition is a graph of equilibrium phases, a graph of equilibrium phases and solubility. Okay, they are soluble. Okay, the alloys are soluble. Limits for an alloy system. So all these are, they are make this a definition. It is not the main component. Okay, a graph of equilibrium phases and solubility limits for an alloy system. Okay, now this is where it's much more important. As a function of composition and temperature. Okay, so three terms which is important here is phases. Okay, a graph of equilibrium phases and solubility, definitely, because it's like when it's an alloy, it is soluble at different levels. For an alloy system, as a function of composition and temperature, this is what you have to know. If one side it is composition, okay, one side is composition, the other side it is temperature, and there is a phase change. Okay, there is a phase change, liquid into solid, and or it's liquid to solid. This is what is the phase diagram. I don't think it's going to be any difficult. Okay, you understand this first area, this first diagram. Okay, first we considered single alloys separately, and then we changed the compositions, mixed them. Okay, mixed them, and we had solubility. Okay, we solubilized them, and we got different equilibrium phases. Okay, and we saw what is the exact when you consider a particular composition, what is the melting ranges, and we connected them. That's it. Okay, and the purpose, once again, identify the phases of an alloy at different composition temperature. Okay, now it's I don't think it's going to be any complicated. Okay, when you get this kind of questions. Okay, note this graph, and what is the purpose? Identifying the phases. So that's what I told you. At different temperatures and composition, you should be able to identify what phase it is there. Okay, it's very easy. Okay, that's it. Okay, that's it for this phase diagram. So I'll stop it here. We'll have some other topic discussed in the next lecture.